Okay, hello everybody. Today I'm planning to cover a new, well, it's not a new, but some alternative theory to gravity, um, which I think is quite interesting because it makes claim to solve several important problems. Like first of all, it's renormalizable. Second of all, it has something to say about dark matter, which is another problem with Einsteinian gravity, and even things like dark energy. So this is the paper which I was planning to review. I came across it actually completely by accident. I never heard about it. Well, I mean, I heard about conformal gravity, of course, that such action exists, but I have never heard that somebody considered to be a serious alternative to Einstein-Hilbert action. I didn't know that there is some reasonable chance it could be in agreement with experiment. So yeah, this author, Philip Mannheim, I don't know how to pronounce his name. So it turned out he was working on this theory for a very long time. I will show you at some point the manuscript which has started this whole activity, and he will like gradually is trying to make the case for it. So yeah, and here's some sort of review of his efforts. Let's see why he thinks it interesting. So at first he noticed that, yeah, he agrees with main Einstein's ideas and that, yes, gravity is geometric, it's determined by curvature, and particles follow the geodesics. But he noticed that, well, actually, the way we test it is through Schwarzschild metric, right? We just know that, well, we know the solution of the Einstein equation, spherical symmetric Einstein equation, and we use it to measure the deviation of Mercury orbit from Newtonian physics. That's how we actually tested. And he points out that, well, this solution is not really unique for Einstein-Hilbert action. That you could have other gravity actions which would reproduce the same solution. So yeah, so he argues that, yeah, this is the Einstein equations, that one example of such theory is what's called conformal gravity. It's built out of square of the Weyl tensor. The Weyl tensor is basically traceless component of the Riemann tensor. As you know, Ricci curvature is its trace, and its physical meaning is the information about how the volume of infinitesimal infinitesimal parallelogram changes when we transfer it across like some small loops or something like this. And the Weyl tensor is precisely the opposite of it. It doesn't care about the volume. It only cares about how angles change. So that's why it's related to conformal geometry, and it transforms covariantly under Weyl transformations. So if you just rescale the metric by keeping all angles the same, the Weyl tensor will just get multiplied by this some function. And in fact, it turns out in the fourth space-time dimension, its square, trace of its square, could be integrated over the whole space-time, is a scalar. It's which is also a Weyl invariant. So this action, yeah, it's obviously a scalar under diffeomorphism, but also has additional symmetry. I don't know whether he would write it down here somewhere. It's a it's a symmetry of multiplication of a metric by an arbitrary no vanishing function. I call it Weyl symmetry. Weyl symmetry. So yeah, that that's action, and he also noticed that because of some identities which also are unique for 4 dimensions, this integral could be written as the integral of some quantities expressed only in terms of Ricci curvatures. Basically, the difference between them is a total derivative, some which corresponds to some topological invariant. And therefore, actually, when we calculate the equations of motion for this action, we see that Ricci tensor equal to 0 is a tautologically solution with vacuum equations. So indeed, any equation, any solution of the Einstein equations in the vacuum also automatically would solve these equations. So if we actually just want this solution, we could get it. No problem. But of course, it has many more solutions because it's high derivative action. And we'll talk about what kind of problems it brings about later. Yeah, so by the way, if you try to insist on having this Weyl invariance or conformal invariance, how he called it, the cosmological constant term will be prohibited. He probably tried to use it to explain why in real world cosmological constant is so small. But I probably will talk about it later. However, it could be easily seen that de Sitter vacuum is a solution of this conformal gravity equations, because de Sitter metric is conformally equivalent to flat one. So we could have a cosmological constant in this gravity like automatically. Yeah, so here he also actually makes an interesting observation that which serves as a motivation for this action. He points out that if you just imagine theory in, like, say, flat space of some fermions or any matter which has this Weyl symmetry, if you try to gauge it, we would actually automatically reproduce the same action for the fermions as coupled to general relativity. So the metric could be understood as a gauge field for this Weyl transformation of a fermion, which is kind of interesting observation. I have never thought about it before. That gravity could be understood both as gauging diffeomorphisms and as gauging of Weyl transformations. I don't know whether it's important for anything, but I would just want to keep this remark. And he also notices that there's the Dirac equation, master Dirac equation, precisely has this Weyl symmetry because the action is invariant at this higher, bigger group, which is the symmetry group of the slide cone, which is precisely the conformal group. So it's another interesting observation, which I also kind of thought about it. I don't know whether it's even correct, but it seems like he sees this Dirac spinner in dimension 4 as a Weyl spinner for the conformal group, which is also kind of very unusual thought. And he also noticed this that if you try to integrate out fermions in this action, because of conformal invariance, the Einstein-Hilbert term will not be generated. What will be generated is only the conformal invariant term, the conformal gravity with infinite coefficients, of course, to will be divergent, plus the Maxwell term. If you couple it to electromagnetic field as well. Okay. Well, now it's also worth discussing what could be the source of such gravity, because as you know, if you just consider Einstein gravity, it already constrains its source, the energy momentum tensor, to be covariantly constant, right? Which is meaningful, just the conservation laws where it is. In this case, the energy momentum tensor of matter has to be covariantly constant and also traceless. So the matter has to be Weyl invariant as well. But this means we could not have any non-dynamically generated mass terms. So if you want to couple this seriously to a standard model, we have to get rid of all the massive parameters in it. And actually, I found a paper where this is done. Let me actually briefly review it as well. So yeah. So here they just noticed that indeed standard model is actually indeed nearly conformal, has nearly conformal invariance. Conformal invariance is only broken by the explicit mass term for the scalar fields. And in this paper, they basically try to realize the same patterns required to match observed phenomenology, right, observed physics on the collider without explicit mass terms for the Higgs field. And they actually succeeded, at least according to their claims. I don't know, I haven't checked it. So the Lagrangians looks like as follows. It's only the interaction part. They meet the kinetic terms. So this is basically, as you can see, quarks and leptons, left chiral quarks, which are doublets, and SU2 weak, right? As usual. And this is a right chiral, up and down quarks. So phi, big phi, is a Higgs field, which is again charged on the SU2. But we also have here a second Higgs field. This phi, small phi, which gives mass to neutrinos. We basically have to have it. As you know, neutrinos, they don't, the right neutrinos, they don't acquire mass through Higgs mechanism. I mean, you have to handle them separately. So therefore, additional Yukawa coupling is added to this new real scalar field, and this new real scalar field also has a quartic potential, but they both don't have a quadratic term because it would violate conformal invariance, Weyl invariance. So yeah, so they analyze this action. And they calculate the one loop effective potential for it using dimensional regularization, and that's how they get this answer. And the some scale v dimension full parameter appeared right under these logarithms. Yeah, which they're gonna use to generate mass scales dynamically. Then they basically say that this problem is kind of difficult, so they have to use numerics. But the claim is they were able to find the range of the new parameters, lambda 1, lambda 2, lambda 3, such that they reproduce the observed Higgs mass, as far as I understand. And in fact, they even claim, that if they run the full randomization group analysis, that this theorem is UV complete. Is UV complete, and also it's stable, means that there is no coupling constant became negative anywhere along the RG flows. So yeah, basically this means this theory that the standard model in this form could be in principle coupled to conformal gravity, serve as its source. So yes, that's one way I think to think about it. He comes up with some other way. He chooses the path of dynamically generated mass parameter for Fermi field. And then he basically integrates it out and gets some sort of Higgs-like action. Oi. Oh. Yeah, it's running out of battery. Okay. yeah, so basically this, now you ask like where does M come from? Yeah, so because how we could get it if it's supposed to be conformal originally. Yeah, this M is basically arises as a condensate, as a bilinear fermion bilinear condensate in the theory which has quartic fermion coupling. But I don't know, in real world fermions don't have such couplings, so I guess it's just a kind of model. So anyways, there are ways to address it. So the takeaway home message is that if you want to have conformal gravity, you want to have full conformal symmetry, or your matter also has to have it. Now, yeah, he goes on to this speculation, which is quite interesting about what does it even mean to have conformal gravity. Now, if everything is conformal, we don't have classical mass terms. This means all mass in the universe is just dynamically generated. So classically, this means classic is just nothing in the universe. Then just totally vacuum solution. So every all non-triviality in the universe only comes from quantization. That's basically the idea. And now also he makes very interesting point about how to quantize this theory. So he noticed that the equation of motions, right, which will become like a Dyson-Schwinger equation, which should still be hold under the correlation function, look like this, right? It's essentially some energy momentum tensor of gravity. The like you could call like whatever it is, variation of the action with respect to the metric for gravity plus the energy momentum tensor of matter equals to 0. And he says that look, if you try to quantize the gravitational field without matter, so that this thing doesn't exist, we will run into the problem, right? There will be some, if it's we try to quantize it's just a bunch of harmonic oscillators as usual, there will be some 0-point energy, and the average of energy momentum tensor would never be 0. So the whole point is that we need to quantize it together with matter, such that there's vacuum oscillations which contribute to divergences of in this vacuum expectation values expression in matter fields would cancel out the one in the gravity. So he's trying to make a claim that gravity could not be quantized separately from matter. I mean, he will show how it works. Yeah, and the next problem to address that conformal gravity is the high derivative theory. So on one hand, it's actually good because if we treat the whole kinetic term not as a perturbation, but I mean just look at the whole kinetic term with force derivatives, all the loop calculations become way more convergent because it's the propagate is proportional, as you can see, to 1 over k to the power 4. We'll see it in a second. I don't know whether he writes it anyway. Okay. So the convergence is improved, and in fact, as you can see, yeah, I should have said from the very beginning, because precisely because this gravity is conformal, right? The coupling in front of it is dimensionless. here it is. Wait, where it was? Alpha G. It has no dimension, so the theory should be renormalizable. That's the advantage as compared to Einstein in gravity, where the whole infinite series of contour terms will be generated because of all these UV divergences. Here the propagator falls down as 1 over k to the 4, momentum to the 4th power, so there should be no problem. The problem is rather what's called with Ostrogradski ghosts. He talks about it for like simplified model with scalar field first with higher derivatives. So if you write down the Hamiltonian for it, you'll see that it's not bounded from below. That's like a standard problem in any high derivative theories. I don't know how to explain it very easily. You could try to do it yourself. If you say have like a action of a particle which depends on coordinate q, momentum, velocity q dot, and second derivative acceleration q dot dot. In order to treat it like normally you would do and write down a Hamiltonian for it, you could just always introduce a constraint, introduce a new variable v, which you call v equal to q dot, and reduce Lagrangian only to the Lagrangian with first derivatives. But then you have a constraint. And if you write down the Hamiltonian, you'll get this linear term from it. So the action is never bounded from below. So that's why people generally consider these high derivatives Lagrangians to be unphysical. And he explains how to solve this problem, how to go around it in some cases. So there is a paper which he wrote with a co-author. Yeah, I think this one. I'm not gonna explain it for conformal gravity because it's difficult, but I'll explain it for this simplified model, how this problem is solved. This is just a toy model. As you can see, it's called Pace-Uhlenbeck oscillator. It has this higher time derivative term in the action. And if you're not the Hamiltonian, you clearly see that it's not bounded from below. It has this additional linear term. So if you try to quantize it, you get something like this. Where A and A dagger, A1 and A2 are two like creation annihilation type of operators. But as you can see, they have like the opposite commutation relations, and here they come with opposite signs. So that leads to a problem. Yeah, as you can see, he says that there are two possible realizations for the theory, like how to build a Fock space. If you take A1 and A2 to annihilate the no particle state omega, the energy spectrum is unbounded below. And in this case, omega is a ground state energy with this energy, right? However, in this case, the excited state, which lies at the energy omega 2 above the ground state, has a Dirac norm negative. So that's a problem. On the other hand, if A1 and A2 dagger annihilate the no particle state omega, then the theory is free of negative norm states, but the energy spectrum is unbounded below. Both of the outcomes are unacceptable and characterize the generic problems that are thought to afflict higher derivative quantum theories. So yeah, and how he solves it. basically he noticed that, well, we can look at this problem in coordinate representation, try to solve it, try to find the wave function explicitly. And he says, look, the wave function of the ground state has this explicit form, and it clearly is unbounded along the z-axis. So that's how this problem shows up. And this means that the momentum pz was actually not Hermitian operator. However, we see that it diverges for some values of z, right, along the real axis. But there's a whole stock wages rotated 90 degrees away from it, where the wave function is well defined and converges. So we need to perform a change of variables, basically 90 degree gradation, to make the wave function well defined. But this will make Hamiltonian explicitly non-Hermitian, right? We see it's just complex valued. So yeah, it seems like should be a problem, right? We want the eigenvalues of the Hamiltonian to be well, our energy levels, so they have to be real. And usually we get used to the fact that if in diagonal basis we find like real eigenvalues, means the matrix is Hermitian, right? So yeah, that's true, but the opposite is not true. In fact, the Hamiltonian turns out to be the Jordan block form, so it still has real eigenvalues, but it's not Hermitian. And I think it's a very interesting situation, which I've never thought about before. I think that's what happens. Actually, I'm not sure in this case. Yeah, in this case, he said that this weird operator, which we could use to conjugate a Hamiltonian to see something over at least manifestly real positive spectrum. I guess, yeah, that's probably the idea. And now this intertwiner will appear in our definition for the norm. So the wave function needs to be adjusted, or in other terms, the norm should be adjusted. So the resolution is just changing the norm. So you rotate the contour and then you change the norm of your wave function and making the theory physical. I don't know what you think about this trick, but they use the same here for conformal gravity. Yeah. So as you can see, if we know that H has real eigenvalues, doesn't mean that H has to be Hermitian. It has to be Hermitian only up to this conjugation by V. And this V is analog of exponent to the power omega in this case. Oh, sorry, Q, or how it called, I don't know. Yeah, we need to introduce new scalar product, and that has helped us solve the problem, which is something quite interesting. I have never thought about it before, that you could have such a situation. Of course, in this case, it means that the metric fluctuation has to be complex, and it seems very unphysical, but he claims that we can't really distinguish it because it can always be absorbed into the definition of constants, coupling constants. I don't know. I mean, it seems like if you couple it to matter, it should make a difference. So this is strange, and I don't know. Maybe I should ask the author how does it work. of course, it's very unusual that he considers the metric to be complex for quantization purposes. So in the path integral, we'll be integrating over complex values of g mu, purely imaginary values. That's kind of strange. So yeah, then he goes on to talk about how to cancel these divergences, actually, how to quantize this gravity in together with the matter fields. And he just says how it works in practice. Gives an example with fermions. Yeah, so Kami nu is like trace reversed metric, fluctuation of the metric. And yeah, he quantized it. This is our modes. As you can see, yeah, the Hamiltonian is clearly over Jordan block form because it has this terms linear in X, which are kind of weird, right? We never would see something like this in the usual quantum field theory. So yeah, we have this usual modes A and A hat, but also have this additional sublinear terms coming from Jordan blocks B and B hat. And he quantizes it, he finds the commutation relations, and they depend on this additional free parameter Z, arbitrary function. And this function is fixed by this equation, by the Dyson-Schwinger equation, basically, which the divergent part of it, which requires divergences to cancel out. So he wants the divergence in the vacuum expectation value of the method and the momentum tensor, which he calculated here for fermions, to cancel out with the divergence in the energy momentum tensor of gravity, of the conformal gravity, which he called W mu 2, which is proportional to Z. So he found that Z is equal to 1 from this relation. So yeah, that's his idea in practice. Here he makes remark about 2 dimensions, I think, that, but which I'm not going to review, that 2-dimensional gravity is not purely topological, because if you quantize it, there is something non-trivial there, I don't know. And now he goes on to talk about how to get the cosmological constant from the vacuum expectation of fermion bilinear. So in this case, it's basically also dynamically generated. Yeah, he used a simple example of 2 dimensions, and in 4 dimensions, like he, as an example, was trying to use quantum electrodynamics because he doesn't have like a 4 fermion interaction, which should be conformally invariant, right? It doesn't have 4 fermion conformal invariant interactions, so he tried to use quantum electrodynamics, and he hopes that it has like a conformal, like has a fixed point energy flow, but I'm not sure about that at all. I don't know. In fact, I found that there is a proof that there is no such fixed point. So I don't think it's a big problem. He could use another theory as a model still. But anyway, it's just an example. Yeah, and here we finally get into the most controversial and difficult part, the dark matter problem. So, well, the whole story started actually from this paper by Mannheim and Cousins, which I have here. I think so. As you can see, it published in 1988. So here just kind of reviewed it. It's basically a spherical symmetric solution of this conformal gravity. They found it has additional linear term here in this I mean, the equation is of fourth order, so you actually have two more additional constants, and he just ignored one. I don't know whether they didn't write it here. Yeah, here it is. This additional, this is a full solution. This additional term, this one is a cosmological constant. As I already said, that the Sitter solution is a vacuum solution of the Weyl gravity, and additional linear term. And it turned out that this additional linear term is what's needed to explain galactic rotation curves. At least for broad class of galaxies. So there was a real hope that conformal gravity is actually just better than Einsteinian gravity. Just think about it. It could be nicely coupled to conformal version of the standard model. It's renormalizable, and would also, I mean, explain the dark matter, and has a cosmological constant built into it automatically. So yeah, that's really nice. I will actually talk about it more because there was a lot of pushback on this. But before we end it, yeah, he makes final remark connecting his paper to 't Hooft results, where 't Hooft noticed that actually you could always obtain conformal gravity from Einstein-Hilbert action by integrating out the part of the metric. So if you just make a change of variables, like say you start with Einstein-Hilbert action, you will get let's say you have a metric G mu, and you make a change of variables. G mu equals omega squared times new metric G mu hat. Then in these new variables, you just get a metric Einsteinian action. What you will get is basically this new scalar omega conformally coupled to curvature, conformally coupled to the metric. Because well, tautologically, right, this G mu hat action action of G mu hat is the variable G mu hat is only well defined up to rescaling, simultaneous rescaling of G mu hat and omega. So there is just a manifestly Weyl invariance here. So clearly this new scalar omega will be conformally coupled to gravity. And then if you integrate it out, you will get a conformal action with infinite coefficient. As the same one which fermions give. So of course, I mean, if you look at 't Hooft paper, he has a whole discussions about what does it mean. So of course you expect it to be divergent. It's not like Einstein action is equivalent to conformal gravity. But maybe there was a hope that that has some sort of deep interpretation. I don't know. But I guess this link is left pretty unexplored. I don't know what it actually means, but it's pretty interesting. Of course, also not clear how the path integral measure changes as a result of this calculation. Yeah, so that's a paper by Philip. As you can see, just a review of his work since 1988 was the first time posted this result. For galactic curve solution. Yeah, and since then there was many discussion about this. And yeah, you could already ask questions even yourself, like as you can see, these parameters beta and gamma, they are related to some function f, which is supposed to encode like the density of our source, right? So it's not clear even like how it's related to the mass of the source, to the total mass. Like we know that inertial mass is equal to gravitational mass, and this parameter beta, it's not clear how it depends on each source. It's not clear that this relation actually holds, at least not clear to me. Also, he mentioned that because the equation is fourth order, it's no longer true that potential at the distance r from some source only depends on matter inside the sphere of radius r. It's all the force even will be affected by the matter outside of this region, which is very strange, right? It means like the whole matter in the universe might affect what's happening in next to your, I don't know, little sun or something. So it's not something we get used to in like Newtonian approximation, neither in Einstein theory. So this part is very bizarre. And in fact, I found like many complaints about this. Like say, the biggest criticism to the theory yeah, came from here. I don't know if it opens. Well, okay. Let me try to find it from scratch. So, yeah, okay. It doesn't open, but okay, it opened here. So yes, they mentioned several problems. Ah, wait, it doesn't open. Oh, it's awful. How it opens here, it's terrible. Yeah, so here's three problems which they mentioned. The first problem is related to the fact that Bach tensor is trace-free. Therefore, the energy momentum tensor is trace-free also. It's hard to see how normal matter with non-zero rest mass, example sun, can be modeled in such a theory. This problem is also related to a vacuum solution because its boundary conditions have to connect to an interior solution. See the third problem below. So okay, yeah, that just exactly what we discussed before, that all mass has to be dynamically generated, so it's all came from quantum effects. The second problem is also related to the conformal invariance of the theory. Since the left-hand side of the Bach's field equation, Bach's field equation is the equations for the gravitational field, transforms homogeneously under conformal transformation. The metric, as well as any other vacuum solutions, remain a solution if it's multiplied by a conformal factor. Therefore, the time-lag geodesics are not fixed horizontal geodesics are, and we need some additional information to determine the real orbit of motion of a massive test particle. So yeah, that's, I don't know, indeed, it seems like the action have a conformal symmetry, this Weyl symmetry, but the solution not necessarily have to. I don't know, or indeed it's not clear what the particle motions should look like in this theory, because it doesn't have the Weyl symmetry itself. So yeah, one solution I think is offered by Maldacena. Try to find it. So he just noticed that if you consider the conformal gravity with additional special boundary condition, Newman boundary condition, this boundary condition will cut out solution of Einstein gravity from all possible solutions. Yeah, here it is. He just uses someone else's result where he just writes the metric. Yeah, he said that it turns out that the metric of an Einsteinian space, which is asymptotically de Sitter one, looks as follows. And he noticed that there is no linear in Z coefficient. So if you rescale it by the factor of Z square, because you can if it's a solution of a conformal gravity, you could just say that the Einsteinian space will satisfy the additional condition Tz of G at Z equals 0 equals 0. So it's possible that we have a conformal gravity in the bulk with this Newman boundary condition in this asymptotically de Sitter space, which precisely picks us the solution of Einsteinian gravity out of bigger space of solutions of conformal gravity, and that's potentially could solve this problem in the sense that the Einstein equivalence principle remains the same. Particles just moves along the geodesic, and the usual solution of Einstein gravity, just the solution of Einstein gravity, comes from the boundary condition in the conformal gravity. CSC, and they say the third problem is the most important one. This is the main subject of a paper. As we know, any physical solution of differential equation not only satisfies the equation itself, but also satisfies certain boundary conditions. The above mentioned constants beta, gamma, and kappa, kappa, yeah, should be related to boundary conditions, which are determined by interior solutions and by the behavior at infinity. So they are not completely free to be fitted to observational data, such as the rotation velocity in a spiral galaxy. So they say that, okay, we want to glue the solution to like a vacuum solution far away from the source. I guess that's what they want. And if we impose these conditions with some additional physical assumptions, we obtain this inequality. Find it. Yeah, that the term gamma r is actually always bigger than this the term beta divided by r, the 1 over r term. So they're trying to say that this solution was never in agreement with experimental observations, because yes, you can see if you go back to Mannheim paper, wherever it was. No, here. Yeah, beta and gamma are both determined in terms of subfunction f. So indeed, you can use these estimates here to show that they are related like this. This Saussure inequality. It's quite a simple observation. But this would render the solution physical because it means that it strongly deviates from Newtonian physics already on the small scales, where 1 over R solution should be dominant. So they think that this result is unphysical. I mean, it doesn't make any sense. So there was some pushback against this as well. But I don't think, yeah, first of all, this person also noticed that one way to resolve the original problem, the problem number 1, is to say that the mass is dynamically generated. This means the geodesics equation should be understood differently. The mass here shouldn't be constant. It should be this new scalar field, and this new scalar field is charged in the Weyl symmetry. So the total geodesic equation will actually be conformally invariant. So yeah, that's one way to think about it. However, it just gets very confusing for me. Yeah, so these authors try to take into account the fact that we need to have this dynamical field to generate mass, and hope to save this solution. So they consider the solution of the conformal gravity equation together with this additional scalar field, and they try to show that it works well for our solar system. I think so. Wait, is it true? And also agrees with some prediction of Galileo and Ulysses spacecraft. However, well, there were some criticism of this result as well. The story continues. So these people, they point out that if you actually study conformal gravity together with this scalar field, which is supposed to generate masses, you actually see that this linear term and the potential is unphysical, just stands from the choice of gauge. So by using the Weyl transformation together with the scalar field, it actually eliminated. And so it was never physical. But it actually raises the same question, which actually even Hooft raised in his paper about conformal gravity. What does this gauge Weyl transformation even means? Like, this is not clear to me. Yeah, so that gets kind of confusing. Yeah, but I guess you read it for yourself and see who is right. What's physical, what's not, how is it? So basically, the claim is that the original paper by Philip and Kazans, they ignored the scalar. They found a solution, and they just misinterpreted it. So in the full physical picture, there would be additional scalar, which would eat up this like, I don't know, degree of freedom or something. And in the physical gauge, the linear term and the potential disappear. So yeah, I guess it's somewhat a mess. I don't know. I don't know whether I should read it further. And in fact, you could ask, well, what about other tests? And I found some paper about this. For example, let's assume that Philip is right. Philip and cousins are right, and there would be this linear term in the potential. Does it actually agree with observations? So these people say that they found galaxies, elliptic galaxies, for which it's not true. It doesn't agree with observations. Basically, they say that this term gamma is just not constant from galaxy to galaxy, or even within one galaxy. Yeah, what does it say? Yeah, we discover a strong relation between gamma star and the stellar mass m star in dwarf spheroidal galaxies. The finding implies that the variation gamma star violates a fundamental prediction of conformal gravity, which posits that gamma star should be a universal constant. Yeah, but I actually reached out to the author about this paper, and he said that he doesn't think that they make the calculation correctly. I mean, I reached out to the Philip, and similarly, I showed him several gravitational lensing papers, which like another, and he told me that calculation of gravitational lensing as a theory is just another huge problem. Because the metric is not asymptotically flat, it's not clear how to even define what light lensing is, like what the light bending angle is. And because of that, there was several papers which obtained different results. One with like a wrong sign, where the bending of light became like weaker. So this was very strange. People developed like a new methods, Rindler-Ishak method, to find this correction. And this is a new result, but I don't know was it's even correct. It's so unclear. Yeah, and I think with this new result, they compared that it could not explain the stated lensing, I mean, which we observe. So I guess if you believe that this derivation makes sense, then the theory is ruled out by gravitational lensing as well. Well, yeah, it's worth mentioning there are several conformal gravity inflation papers, which shows that it might work there. Yeah, here it is. And I don't know. Yeah, I don't know how constraining inflation data is to rule this out. So I'm not, because I'm not an expert in it. And finally, the final question you could ask is, what about gravitational waves? Don't they rule out conformal gravity? And by now it looks like they do. So first of all, it looks like the gravitational radiation is just way weaker in conformal gravity. So it looks like it doesn't reproduce the observation from LIGO. And instead, people start to work with some sort of what's called massive conformal gravity, which is kind of weird. It has like a conformal gravity with like opposite sign or something somewhere between these terms. I don't know how it makes sense, but anyways, the actual conformal gravity seems like ruled out by gravitational waves detection. So that's pretty unfortunate. So in summary, yeah, that was a pretty good idea, and it's kind of unusual and brave, right? You just throw away the Einstein term, right? And then hope it's gonna work. And you have renormalizability, you have quantization, and then you even have some prediction for dark matter. But first of all, the physical mean, what is not completely clear, yeah, seems like the lengthening rules it out, gravitational waves rule it out as well. And it might be that the result is just wrong. So yeah, I don't know. But I think like still a lot of lessons learned from it. It's interesting that we usually teach people only theories which we know are correct, but we never teach the theories which turn out to be wrong, and we never explain why they're wrong. Also, it's actually quite interesting that you could consider quadratic gravity in general, where you don't have conformal, I mean Weyl symmetry, but you just have these three terms, and it still will be normalizable, and you will still work with it. And there are people who do it as well, like this one. In fact, Curt Jaimungal recently interviewed him. So I guess this development is not dead yet. However, I don't know how to make it work. Yeah, I guess this video was too long, so you're probably bored. I made it mostly for myself anyway. But I just want to share with you some, unusual quantum gravity approaches. And show that there are some people who are trying to go in some sense against the mainstream. If we could just consider this non-mainstream, because it's still the same paradigm of equivalence principle, action, curvature, and so on. Yeah, I guess that's all for today.